Hi, good morning to all. This is Srikanth Reddy P. lecturer in Electronics and Communication Engineering Department, working as a lecturer in Government Polytechnic, Jogipet. Today we discuss the subject name is microwave communication and television. Subject code is EC405. In this subject, today discuss the topics are state the need for microwave tubes, list the various microwave tubes, explain the working of multi-cavity klystron amplifier, and list the applications of multi-cavity klystron. First topic is state the need for microwave tubes. The conventional tubes such as triodes, tetrodes, pentadodes, etc. can be used as amplifiers and oscillators more efficiently. But these conventional tubes cannot be used as amplifiers or oscillators at high frequency above 1000 GHz or 1000 MHz or 1 GHz because higher frequencies output drops off. That means in general normal conventional tubes like triodes, tetrodes and pentodes can be used as amplifiers and oscillators more efficiently. But at very high frequencies, that is above 1 GHz or 1000 MHz frequencies, 1000 MHz above frequencies, the normal diodes and triodes and pentodes are not used for amplifiers and oscillators because at high frequencies the output drops off. The factors contributing to a reduction of output at ultra high frequencies are circuit reactance, that is interelectrode capacitance, lead inductance, transmit time effects, cathode emission and plate heat dissipation area, power loss due to skin effect, radiation and dielectric losses, gain bandwidth product. That means at above 1 GHz frequency or ultra high frequencies, the frequencies of signals transmitted in a waveguides or tubes, microwave tubes, are depending on few factors, that is circuit reactance, that one is uh, lead inductance, lead inductance or inter-electrode capacitance, and transmit time effects, cathode emission and plate heat dissipation area, power loss due to skin effect, radiation and electric losses, gain bandwidth breadth. These are the factors affecting the ultra high frequencies or above 1 GHz frequency signals. At microwave tubes performs the same functions of generation and amplification in the microwave portion of the frequency spectrum that vacuum tubes performs at low frequencies. That means the microwave frequencies are some functions, same function as generation of amplifiers of normal or lower frequency signals. The microwave tubes was developed when the use of frequency spectrum went beyond 1000 MHz and into microwave range. That means above 1 GHz megahertz, above 1 GHz signals frequency or 1000 MHz frequency signals are called microwave signals. These are used in for microwave tubes for developing these microwave frequency signals. That means the microwave tubes are used for transmitting of microwave frequencies, that is above 1 GHz frequency. The microwave tubes uses transmit time in the conversion of DC power to radio frequency power. The microwave tubes are transist time the conversion of DC power to radiation frequency power. The interchange of power is accomplished by using principle of electron velocity modulation and low loss resonant cavities in the microwave tubes. These are the need for microwave tubes. Mainly, microwave tubes are developed for microwave frequency signal, that is 1 GHz above frequency or 1000 MHz frequency. These microwave tubes are affecting the factors of transmit time, circuit reactance, gain bandwidth product, cathode emission and plate of heat dissipation area, power loss due to skin effect, and radiation and dielectric losses. And these microfrequencies are developed for frequency spectrum above 1000 MHz or 1 GHz in the microwave frequency range. Next topic, list the various microwave tubes. There are basically two types of microwave tubes are there. Microwave tubes are basically two types. One is linear type or O type tubes. Second one is crossfield type or M type tubes. Linear and crossfield or O type or M type tubes are used classified by the microwave tubes. Linear type or O type tubes, the electron beam traverses the length of the tube and it is parallel to the electric field. In this class, both velocity and density modulation takes place, creating the bunching effect. It is also called as linear beam tube or linear type or O-type tubes. That means here the electric beam travels along the length of the tube, along the length of the tubes. The in linear type or O types, the electrons beam or the electrons travels, the electron beams travels or traverse along the length of the tube. It is that means parallel to the electric field. That's why it is called as linear types. In this linear type, both velocity and density modulations are take place, which creating the bunching effect. These linear type or O-type tubes again classified into three categories: klystrons, traveling wave tubes, carcinotrons. Klystrons. The klystrons examples are tube cavity oscillators, reflex oscillators, multi-cavity amplifiers, and extended interaction oscillators. These are the klystrons type. Klystron type. Traveling waves tubes. Example of helix, BWO, backward wave oscillations, coupled cavity, etc. Backward cavity. And third one, carcinotrons. These are the classification of linear type or O type tubes. The second classification is cross-field or M-type tubes. A principal feature of such tube is that electrons travel in curved path. These are cross-field devices where the focusing field is perpendicular to the accelerating of electric field. That means in cross-field or M-type tubes, the electrons are travels in curved path nature. In linear type, the electrons are traveled in along the tube, here curved path. In crossfield, here the devices are focusing field is perpendicular to the acceleration of electric field. Here focusing field is perpendicular to the accelerating of electric field. In linear, the focusing field are parallel to the accelerating of electric field. So linear law we can transmit in along the tube. In crossfield law, the electrons are traveling in curved path nature. In this linear, we can have parallel to the electric field. In curved path, it is perpendicular to the electric field. In crossfield or M-type tubes are further divided into magnetrons and crossfield amplifiers. Okay, magnetrons and crossfield amplifiers are classification of categories of crossfield or M-type tubes. These are two types of microwave tubes, linear and crossfield. Explain the working of multi-cavity klystron amplifier. Explain the working of multi-cavity klystron amplifier. First one is construction. The multi-cavity klystron consists of a glass envelope in which there is an electron gun composed of heater and cathode. After the electron gun, there are two focusing electrodes used to keep the electron beam in the center around the glass envelope. That means in multi-cavity klystron consists of a glass envelope tube. In this, first we starting as electron gun composed with heater and cathode. After that one electron gun, there are two focusing electrodes used to keep the electrons in center around the glass of the envelope. There are two cavities known as buncher and catcher cavities. Between the cavities around the glass envelope, a magnet is used in order to keep the electron beam in the center. At the end, there is a anode is kept at the positive potential with respect to the cathode, and it is used to attract the electrons emitted from the cathode. That means here multi-cavity klystron we discussing. So first we have two cavities are there. One is buncher cavity, another one is catcher cavities. One is buncher, another one is cat. In this buncher cavity and catcher cavity, we place a magnet used to keep the electrons around the glass, keep the electrons beam in the center. At the end, we keep the electron gun which is as positive potential anode. At the left side we use a electron gun, and right side we use it as a collector anode, and in between we use it as buncher cavity and catcher cavity. Two cavities are used. In these cavities, middle we can use it as a magnet. This magnet is used to the electrons with are in center of the glass. A high velocity electron beam is from cathode. It produced, focused and sent down along the glass tube through an input cavity, buncher, a field-free drift space, and the output cavity, catcher, to collect the electrode anode. The input and output are taken from the tubes via resonant cavities. That means the electrons are generated from the cathode, and these electrons are transferred to the glass vacuum tubes. At the starting, we have a catcher input cavity called as buncher, and ending we have the output cavity called as catcher cavity, and at the last end we use a collector anode which is used to attract the electrons. So the electrons are generated by the cathode and collected by the anode to travels via glass in a vacuum tube with two or more buncher and catcher cavities. The bunching process in two cavity klystron is not perfect, since large number of electrons which are out of phase arrive in the catcher cavity between bunchers. There are maximum gain of 20 dB can be achieved. To obtain a higher gain, more than two cavities are employed practically. This arrangement is called as multi-cavity klystron amplifier. That means in bunching process in two cavities, klystron is not perfect since large number of electrons which are out of phase arriving in a catcher cavity. So in two cavities, buncher and catcher cavity, the maximum gain is 20 decibel. At a very high frequency of high electrons are generated. In this situation, we improve the gain. We have to use more number of cavities in between bunching and catcher. So it is called as, this arrangement is called as multi-cavity klystron amplifier. So the construction here the construction of multi-cavity klystron amplifier. Here we show the diagram. In this left side we have a cathode which contains electron guns and heater, and right side we used as collector as anode. Cathode is generating for electrons, anode is collecting the electrons. In between cathode and anode we use as a glass tube or vacuum tube. In this vacuum tube we have two main cavities. One is bunching cavity, is taken as the input, and catcher cavity, which is the output. Here input taken as the RF input for buncher cavity, RF out for catcher cavity. In these two cavities between the two cavities we used as magnet between the glass, which is used to center of the electrons beams travels. The electrons are traveled in a center in used for magnet. Here two cavities are used to generating our 20 decibel maximum gain. To increasing the gain, we used in more number of cavities in this one, buncher and catcher cavities. So this type of arrangement is called as multi-cavity klystron amplifiers. So more cavities are used to increase the gain of the amplifier. This is the construction of multi-cavity klystron amplifier. Next, operation or working. When the switch is on, the electrons start emitting from the cathode. That forms the electron beam. This high velocity electron beam is focused and moves uniform speed towards the collector or collector electrode, which is at high positive potential with respect to cathode. That means here when switch is on, the electrons are emitting from the cathode or electron gun. The cathode is generating the electrons. These electrons are very high velocity. That means electrons velocity is approximately light velocity 3 into 10 to the power 8 meter per second. So this velocity is very high. These electrons are moves uniformly to the vacuum tube or glass, and which travels to the end of the vacuum, which contains collector electrode, that is anode, which is very high positive compared to the cathode. The beam passes gap A in the buncher cavity and RF input signal is be amplified, is applied to the buncher cavity with the help of loop coupling. As a result, the beam of the electrons will be formed near to the buncher cavity and reaches other cavities with highly excited. It is then allowed to drift freely without any influence from RF fields until it reaches a gap B in the catcher cavity. Due to its strong field strength, the excitation of electrons takes place and will get an amplified output from the catcher cavity. That means here in this diagram, the first cavity is called as buncher cavity. In this cavity, we given as RF radio frequency signal as the input, which given to the input of the buncher cavity. These input signals are given to the buncher cavity through vacuum or glass. In this glass, the electrons are emitted or traveling from cathode to anode, and this RF signal also to touches the electrons and travels along the vacuum tube and reaches to the catcher cavity, and these electrons are amplified by the electron's velocity, and these amplified velocity is signals are out from the last end of the cavity, which is called as catcher cavity. So the RF signal is amplified by the flow of electrons, and these electrons are reaches to the collector and electrode anode. In this way, the RF signal is amplified. If the number of cavity increases, the gain of multi-cavity klystron is also increases. The beam is then collected by the collector electrode. That means if we have starting as buncher cavity, ending as catcher cavity. In this, two cavities are used to produce 20 decibel gain. To increase the gain by improving the number of cavities. If the number of cavities are increases, the gain of the multi-cavity klystron also increases. Here the diagram shows the bunching effect. Voltage across gap, position of gap A, voltage across a gap A, and position of gap A. To comparison of the electrons from bunching cavity to catcher cavity. The electrons are traveled from buncher to catcher. How much time we taken, how much velocity it can be taken. These all are shown by the diagrams. Similarly, an early electrons EE that passes the gap A is slightly before the reference electron ER is subjected to maximum negative field. Hence, this early electrons is decelerated and travels with reduced velocity V0. This electrons EE falls back and a reference electron ER catches up at the early electrons. That means in first air gap in buncher cavity A, the RF signals are touches the electrons B. When RF signals are touches the electrons energy is taken by the RF signal, and the RF signal is amplified and travels along the electrons from starting position to ending position, buncher to catcher. In this situation, the electrons are lose some energy, so the electrons are falls down These electrons energy is taken by the RF signal, and the RF signals are amplified and it travels to the buncher cavity to catcher cavity. The falling electrons are back and reference electrons ER, and these falling electrons are again amplified by the starting or generated by the electron gun electrons, and these are again amplified and transferred towards the anode catcher cavities. As a result of these actions, the electrons in the bunching limit between point A to C gradually bunching together as they travel down the drift space from gap A to gap B. The pulsating strength from electrons passes through gap B and excited oscillators in the output of cavity or catcher. That means we have two gaps, gap A from taken from bunching cavity and gap B taken from multi cavities, and last one is again taken gap C. If the electrons are taken the electrons are given the energy to the RF signals, and it is also amplified by the cathode generated electrons of next generation signals. These electrons are travels toward the working tube and reach to the catcher C, which is the output of cavity. So the gap A to gap C or gap A to gap A end of the catcher is used to collect the signals. The bunching occurs only once per cycle, centered around the reference electrons with proper design. Optimum gap width, anode to cathode voltage, drift space length, a little RF power applied to the buncher cavity results in large beam currents at the catcher cavity with a considerable power gain. That means if this bunching takes only once per cycles, center around the reference with proper design to the multi-cavity distance by increasing the drift space length or optimum gap width or anode to cathode voltages. These are used to increase the bunching capacity, or RF power applied to the puncture cavity results large beam current. These large beam currents enter to the catcher cavity with considerable for power gain, increasing the power gain. This is the operation of multi-cavity klystron amplifier. Here the diagram shows. Explain the topic by the diagram. Here, multi-cavity reflex klystron amplifier. Here, in this diagram, the starting left we used as cathode, which contains electron gun and heater. The electron gun and heater. Whenever the switch is on, the electron gun is generating the electrons which are traveling towards the glass or vacuum tube through the collector, which is as highly positive compared to the cathode. So anode is a very highly positive voltage compared to the cathode. So cathode is taken as negative, anode is taken as positive voltage. In this diagram, we have two or more cavities are there. First, we discuss about two cavities. First one is buncher cavity, that is input cavity. Last one, end one is catcher cavity, that is output cavities. In buncher cavity, we given as RF input, radio frequency input signal is given as in buncher cavities. The RF signal is coming from input of the buncher cavity which touches the electrons. The electrons are moving towards the center of the glass by using the magnets. The electrons are transmitted from cathode to collector at very high frequency and very high velocities. The RF signals are touches the electrons, then the RF signals are absorb the energy from the electrons, and which RF signal is amplified and transmitted through electrons and towards the gap A to gap C. Here the RF signals are transmitted towards to the buncher cavity to the catcher cavity. Then the after the catcher cavity, the electrons are attracted by the collector, that is anode. Here the amplified RF signal is collected by the output of the cavity, that is called as catcher cavity. This RF signal is in this way amplified and transmitted from buncher cavity to catcher cavity. In one time we take it as two cavities. These two cavities produces maximum gain as 20 decibels. If increasing the gain by using more number of cavities, if more number of cavities increases, the bunching takes place from A to B or B to C, B to C, C and last one A. In this way, more number of cavities are used to increases the gain of the multi-cavity klystron amplifiers. So this one is the multi-cavity klystron amplifier. And last topic is list the applications of multi-cavity klystron. These multi-cavity klystrons are used in TV transmitters. These multi-cavity klystrons are used in satellite earth stations. These multi-cavity klystron amplifiers are used for power amplifier at 6 GHz, and these multi-cavity klystons are used in radar transmissions, TV transmissions, earth stations, satellite earth stations, and power amplifiers and radar transmitter. These are the applications of multi-cavity klystron amplifier. Briefly discuss the topics once again. State the need for microwave tubes, list the various microwave tubes, explain the working of multi-cavity klystron amplifier, and list applications of multi-cavities. Need for microwave tubes. Microwave tubes means the conventional tubes like diodes, triodes, tetras are used for general amplification and oscillator purpose at lower frequencies. At very high frequencies like 1 GHz above frequency or 1000 MHz frequencies is signals above frequency signals are designed separately for microwave tubes. These high frequency signals are transmitted purpose used to design microwave tubes because high frequencies output drops is more output drops of these microwave tubes. That means the microwave tubes contains microwave signals above 1 GHz or ultra high frequencies. These are affecting the factors or these are affecting factors are circuit reactance and transmit time effects, cathode emission and plate heat dissipation area, power loss due to skin effect, radiation and electric loss, and gain bandwidth product. These microwave frequencies are above 1000 MHz or 1 GHz frequencies are used to transmit for microwave tubes. These are high velocity electron velocity modulation and low loss resonant cavities are used for the microwave tubes. Various types of microwave tubes. Microwave tubes are basically divided into two types, linear type and crossfield type. Again, linear type is also called as O-type tubes. Crossfield type is also called as M-type tubes. In linear type, the electron beams travels along the length of the tube. In crossfield, the electron beams travel in curved path. In linear, the electric field is parallel to the along the electric field. The electrons are parallel to the electric field. In cross field, it is perpendicular to the electric field. In linear type or O-type tubes are again divided into klystrons, traveling wave tubes and calcinotrons. And crossed field or M fields are again divided into two categories, magnetrons and crossfield amplifiers. Next, explain the working of multi-cavity crystals. Here we show the diagram of multi-cavity crystals. The construction and working of multi-crystal. Here the diagram shows the multi-cavity crystal. Here left side we taken as cathode which contain electron gun and heater, and right end we contains as collector as anode. The anode is very high potential compared to the cathode. And we have three cavities are there. First one is input cavity, is called as puncture cavity. Last one is taken as output cavity, is called as catcher cavity. We have two cavities. Okay, the between the two cavities we used as magnet. These magnets are used to centralize the electrons. The electrons are within center of the vacuum tube or glass. Here when switch is on, the electron gun generating the electrons. These electrons are transmitted at very high velocity towards the collector or anode. This anode is collecting the electrons. Whenever we given as RF input to the buncher cavity, the RF input is coming from buncher cavity to the glass or vacuum tube. The RF signals are touches the electrons and the RF signals are amplified by the electrons velocities. The electrons are taken as bunching. Whenever the electrons energy is given to the RF signals, the electrons are lose their energy. then the electrons are downwards, and whenever cathode generating a very high frequency electrons. So here signals are up and down movement are taken. This is called as bunching process. The RF signal is amplified by the electrons and which are travels along the electrons towards the collector. At the end, the collector collect the electrons. That means anode attracts the electrons. The RF signal is amplified by the electrons velocity, and the maximum gain is 20 decibel. If increase the more number of cavity, the gain will be increases. In this way, the multi-cavity crystal amplifier is working. Applications of multi-cavity crystals. It is used in TV transmitters, satellite earth stations, and power amplifiers in radar transmitters. These are the applications of multi-cavity crystals. Thank you to all.